So we now have a 45-minute session, yeah?
Yeah, that's right.
Okay, cool. So let's do the first part of this, and then we'll have our mingle break or something like that, and then we'll come back to things. Cool. Right. So last time we talked about why we might even want to fix a theory. We talked about SMT-lib and how we describe what theory we're fixing, and also how we make use of that, how we say things in terms of those theories, or specifically as logics which bunch together multiple theories. So now I'm going to go on, I'm going to talk about one specific theory. Right, so a bunch of people posted in general saying that they did software verification. So this is a question specifically aimed at them. And if you can post your answers into the Zoom chat, then I will keep a quick eye on those, and let's see how many of them we get. So this is a program. So the idea is that it takes in n, which is the number of sample points it should take, a start point and an end point. First off, it checks if n is 0, and otherwise it, and also you need that end is larger than the start. Otherwise, what it does is it works out the increment, and it then just works from the start point by increment, and it just samples at each location. So it's literally goes, how long's this? We need like 4 samples in that. Okay, divide it by 4. I'm going done. Okay, that's what the program does. So answers in the chat. How many bugs are there in this program? How many things are wrong with this program? Does it always sample endpoints? Could it sample more? Could it sample less? And so I'm particularly, this is the point where if I was doing this kind of talk live, I would be finding some professors and putting them on the spot, making them answer the question, which is really mean. But if you're up at the front of lecture theatre, you can get away with that sort of thing a bit. So particularly, I'm interested in answers from anyone who's tenured or, career track academic. How many sample points will we take? In fact, even worse question, does this thing even terminate? And it's all gone silent. So is it silent because we're getting to mid-afternoon and everyone's just like really done, or does anybody think this might be a non-trivial question? Like, can I have a brief show of hands in the participant? Put your hand up if you think that this question might actually be quite difficult to answer. How many sample points do we get? Does it even terminate? Can you put your hand up if you think this might be a hard question? Cool, one person does. So if you think it's easy, just post in like the chat. If you think it's hard, put your hand up. And this way we get to see if everyone's come back from the break. Okay, so we've got a couple of votes are hard, but I'm still not seeing anybody who says that they do software verification answering this. Does that loop terminate? How many sample points do we take? Okay, well, let's come back to it. A lot of people seem very uncertain about this one, so we'll come back to it. So, because I'm fundamentally quite a lazy person, when I'm faced with a problem like this, I'm like, could I get my computer to solve it for me? And because I know a little bit about software verification, I'm like, actually, maybe I can, but if we're going to automate answering questions like this, does it terminate? How many sample points do you get? Is it always there? If we're going to automate questions like that, then what we'd really need is a box that can reason about floating point. And specifically, we need it that it's got to be bit exact. So it's got to do exactly what the hardware does, because part of the reason why this question might be regarded as being difficult is that it depends a lot on the detail of floating point. Like if our solver's detail of floating point is different to our hardware's, it's just not going to work. Like, your solver will be like, oh, this could happen. And then you run it on the actual hardware and it's like, no, it really doesn't. Okay. That wastes everyone's time, makes people not confident the solvers are correct. So we need it to be exactly what the hardware does. We need it to be precise. We need it to say SAT or unsat. So SMT solvers are allowed to say unknown. This is how we get around some of the decidability issues. But in this case, we really, really want just SAT or unsat. We also ideally want it model generating, so that if it says, hey, look, there is this case when this thing would just get into an infinite loop, I'd really like to have the input vector that causes that. And we also want it to be automated and, fast and just work out the box. Yeah. Simple, right? Cool. So what else, if we had one of these kind of proofs, what else could we do it? So I've seen some people say that they're interested in symbolic execution. So obviously path feasibility, test case generation. You need this kind of tech. Generation of special values. So we will come to this in a minute, but floating point has some additional numbers that aren't quite the same. Some placeholder values, infinities, this kind of thing. And it's quite easy to not handle them correctly. So we use this kind of solver to go, okay, look, your code, if it's fed these particular inputs, it could crash or do things. Numerical instability. So cases when if you evaluated this computation in real, then the answer would be significantly different to what happens when you evaluate it in float. We could find language level undefined behavior issues. So famously, the loss of Ariane 501, one of the first flagship of the Ariane 5 rocket fleet, was caused by undefined behavior related to floating point. Okay. That was the spark, as it were. But yeah, we could check for that. Things that are kind of borderline, but with that, it's sort of getting there. Verification of hardware floating point units. So this is the famous Intel FDiv bug, which, now I think about it, the bug may well be older than a number of the people attending this talk. So Intel shipped a processor, it was version of Pentium 1, in which floating point divide did not actually produce the correct answer in a small number of cases. And they botched the sort of PR on this by telling people, oh, well, yeah, you know, for your use case, it doesn't matter. And I mean, to be fair to them, they were probably right. But telling a bunch of people who spent a fortune on a new processor that really them getting the right answers doesn't matter was not what the public wanted to hear. I think in the end, the whole debacle and the recall cost them into the billions. I'm sure that there are figures knocking around for this, but yeah, if you're interested in hardware and particularly data path, then the question of how do we verify our floating point units is still challenging. Something about neural nets. I'm not going to say something about neural nets, but Guy will tomorrow. Go ask him. He knows way more about this than I do. Things that we would love to be able to do one day: functional correctness in numerical code and automate numerical analysis. That would be amazing. We're not there yet, but maybe one day. So first off, how many people, again, can I have a quick show of hands in the chat? How many people feel they are confident that they understand floating point? Hand up if you do. I suppose I should probably put a hand up, shouldn't I? Why not? So with India's great reputation for like actually teaching hands-on tech, I'm surprised that people don't cover this in sort of first-year courses. But right, so floating point has this sort of fearsome reputation as it's excessively complex and prone to mysterious behavior.
Martin,
Yes.
there's a question on the chat window.
Yep. Is it possible that increment is so small adding it virtually doesn't change the float? Yes, that is one of the things that can go wrong with the example. There are others. There is a lot wrong with that example code. But yes, that's one of the things. And I'll come to how that could happen in a little bit. Right, so floating point has this horrible reputation for complexity, which is, which I think is in some ways undeserved because for the most part, it's actually quite a well, IEEE 754 arithmetic is actually a pretty well, sorry, the Zoom is being weird. IEEE 754 is actually a pretty well designed system. So I'm going to try and sort of justify why I think that. So first off, let's try and build a number system. So let's assume that we have some finite length fixed size bit strings, okay? And we want to associate those with some real values. So a real number, okay? And we have a mapping that goes bit strings to reals. So maybe we've got 32-bit bit strings, so we've got 2 to the 32 numbers, and we can represent 2 to the 32 reals. Great. Okay, so that's cool. first design problem. If these bit strings are representing reals, then we can order the reals, therefore we can order the bit strings. So there must be a biggest bit string. There must be a bit string that represents the largest real number that we can represent. And yeah, what happens if we add 2 of those up? Well, we're going to have to do something. So design options, we could just wrap it round and, like, you know, you do with integers, and then just kind of go and wrap it round to the other end. The problem with that is that you can't tell when you've made a mistake. You can't tell when an overflow has occurred. Unless, of course, I mean, okay, so if you just wrap around, you just can't tell. We could halt the execution of the system. It doesn't sound like a particularly good idea, because what it means is that we have to always be ready after every operation to kind of stop things. So it means then that we can't necessarily, you know, take these numerical computations and just turn them into parallel and make them parallel, this kind of thing. That's kind of awkward. So okay, so one solution is we could have a special value, or maybe 2 special values, for infinity, you know, for a number that's so big that we can't represent it. So as well as our things that represent reals, then let's add on 2 more points. This would be so much easier if I had a whiteboard. We add on 2 more points for infinities, and anything that gets too big, we just turn into an infinity. Okay, cool. Yeah. But what happens if someone tries to subtract them? Well, that's annoying. I mean, I guess we could put 0, but then again, that means that we get into this world of, we could just miss that overflows have happened. We could say that one infinity is bigger than the other. Like, you know, we could just say, well, that's plus infinity, or we could just say, well, the negative one's bigger, it's minus infinity. The problem with that, though, is that you now have a system where negate doesn't commute through operations, so that doesn't really work. So we could do the same thing again, right? So we could say, let's have another special value, which is, I don't, you know, which is not a number, right? For marking things that just aren't numbers, that are just a mistake. Okay, and then we could have infinity minus infinity being not a number. Okay, cool, we're done. Oh, except we're not, because just as there was a biggest real, or a bit string that represented the biggest real, we'd also ask what's the smallest real, the smallest, a absolute smallest, the closest one to 0. And yeah, if we subtracted one of those from the other, then 2 copies, or, you know, we pick the thing that's nearest above 0, and we pick the next one up. If we subtracted those 2, then we're going to get a number that's smaller than we can represent. Okay, well, look, as long as we've got a bit string that represents 0, then we're fine, right? We'll just, anything that underflows, we'll just turn into a 0. It'll be fine. Does it matter which way it converges though? Does it matter whether this is something it's getting is strictly positive and it's getting closer to zero, or whether it's something that's strictly negative and getting close to zero? Because, you know, if you were, say, computing 1 over x, then if it was converging on the positive side, then you'd want that to go to positive infinity when you divide it by it. But if you're converging towards zero from the negative side, then you'd want it to go to minus infinity. So, solution. We'll have two zeros. We'll have a positive zero and a negative zero. And that will let us tell the difference between whether we're converging from above to zero or converging from below to zero. And that way we can make sure that our signs work and dividing by it's fine. Branch cuts on tangents, that's fine. Yeah, okay, so simple, two zeros. Yeah, okay, there's one more problem. This is not algebraically closed. Can't be, because if we can multiply by, you know, if we've got numbers that are fractions, then we can wind up computing something that's halfway between 2 points. So what do we do then? We've only got fixed length bit strings, you know, because I just said, let's start from the concept. Let's just start by talking about building a number system, a map from bit strings to reals. Right, okay, well, to handle overflow, we need infinities. To deal with weird cases, people doing stupid things with infinities, we need a not a number. To deal with this convergence problem, we need positive and negative zero. But we still, we can wind up generating values that we don't have bit strings for. So we just have to round. We just have to, when we've got a value, we just have to turn it into the nearest thing we can represent. And so hopefully you see with this little round of like, well, these things these are all problems that turn up as soon as you try and design a number system where you've got fixed length bit strings representing some reals. And so things like you need infinities, things like you need a not a number, you need two zeros, you need rounding. They're all kind of inevitable conclusions. I mean, there are a few other solutions to how to do this sort of thing, but to be honest, many of them wind up being worse. So in that sense, the design of IEEE 754, which is the kind of float that you probably have on your computer. There are some other non-standard float systems around, but most of it just follows by like basic necessity of like, well, we have to have addition, we have to have divide represent something. So, okay, what are the actual values going to be? So, floating point. IEEE 754 represents floating point numbers with three big things. One bit.
Martin, I have a quick question.
Sure.
This IEEE 754 standard, and there is this another IEC 60559 standard. So are they the same, or there are some subtle differences?
Right. So I think the second one is the base independent version. I mean, part of the problem, there's a joke coming up about this actually. Part of the problem with standards is there are so many different standards organizations, so you wind up with one standard acquiring the same name acquire many different names. So I would need to look. I think the one you quoted is either one of the other names of IEEE 754, or it's the extension that handles non-binary arithmetic. I need to look. If you message me the standard string, I'll look that one up for you. But yeah, so our representation, we have -1 to the sign bit. Our base for everything I'll be doing today, the base is 2. An exponent and a significand. So what that means is if we've got a number like 7.28125, well, that's a 4, a 2, a 1, and a quarter, and a 1/32. So you turn it into binary, that's where you get your decimal point. And so the thing that makes the system floating point is that different numbers will have the decimal point in different places. So when we have the number stored, implicitly the decimal point is always there. And the exponent allows you to shift. So with this, we have to normalize, we have to skip it over 2 points. And that's why the exponent is 2. So it means that the significand part is always between 1 and 2. Always, small caveat. It's always between 1 and 2. But this can get big. So this means we can represent very large numbers. It means we can represent very, very, very small numbers. Whereas if we wanted to do that with fixed point, if we wanted to have that dynamic range, but have it a fixed point system so that the decimal point is in the same place for every number, then we need a really big, like really big fixed point number. Because as it is, we can have floats that are very high up the range or floats that are very low down the range. So we can have good accuracy on a relatively small float. Whereas a fixed point, you'd need a much, much larger number if you need that dynamic range. So system design point of view, hardware point of view, if your dynamic range is very low, use a fixed point. If your dynamic range is potentially very high, use floating point. Awkward, weird technicality. So this works, right? But there's a little bit of a problem, which is that as you get near 0, so you've got 2 to the minus some number, and as you're counting down here, the difference between 1, 0, 0, 0, 0, 0, 0, 1 and 1, 0, 0, 0, 0, 0, 0, 0. If you've got the smallest possible exponent you can, then the difference between those two numbers is not representable. And that's kind of awkward. And it's kind of awkward because you sort of want that if a minus b is equal to 0, then that means a is equal to b. And if you just use a naive floating point system like this, you don't have that property. And so you can have things where you can't measure the difference between them, but they are different. And that's kind of really painful and counterintuitive. So we also, IEEE 754, and at the time this was controversial, to some degree it still is, also have a very, very small set of fixed point numbers between 0 and the smallest float. And that means that you can always represent the difference between two floats, provided it doesn't overflow. You know, if the two floats have the same size, you can always represent the difference. And so that means that the relative error between things is constant, apart from this small range of subnormals. So, putting all of this together, why, why do I get papers published on this kind of thing? Why is this problem difficult at all? Well, part of it is the combinatorics. I said earlier on, if we want to be able to represent things, we're going to generate values that are between numbers. We need to round. How do we round? There's at least 5 different ways of doing it. Also, we're going to have different kinds of numbers. We've got the normal numbers like we talked about. We've got the subnormals, like these tiny little range of fixed point, so that you can always represent the difference between two numbers. We've got zeros. We've got a pair of zeros, remember, because we want to know about convergence from above and convergence from below. We've got infinities. We've got 2 of them for the top and bottom. We've got a not a number for anything that's just clearly just not a number. Let's divide infinity by infinity. What's that? So just one addition, we've potentially got 125 cases to think about. So as like case by case reasoning, you can do it on a small scale, but once it starts to scale up, like, if we've got 125 there, as soon as we add another operation, we're going to multiply that. Like, the number of possible combinations is just asking, what kind of number is this? Rapidly just explodes. Okay, so this is one of the reasons that makes this hard, combinatorics. The second thing that makes it really hard is rounding. So I said you need rounding because you will be able to generate value. Rounding is what makes the system algebraically closed. You have a fixed number of bit strings, you've got to be closed. If you generate values between two things, what do you do? So the problem is that rounding breaks a number of key ring and field properties. Floating point addition is not associative. Worse, floating point multiplication is not associative either, nor are they distributed. There are fields of research called non-associative algebra. I've yet to meet anyone who actually works on them. I would really like to. I have a feeling they're just going to talk to me about matrices, but basically the consequence of rounding is that it breaks almost all of the maths that you actually want to apply, which is kind of frustrating. But it's worse, so this is specifically for reasoning about floating point, but if you then want to talk about floating point software, you have some additional extra challenges. So one of them is the ranges used. Okay, so say someone's written, you've got some code in to verify, and it's got a double in there, and it's got a double, and the variable's called speed, because it's a self-driving car or something. Okay, so, and you know that this speed is always listed as positive. Well, in theory, that means that you've got 63 bits to think about. In practice, I think you've actually probably only got 16. So range of positive doubles is something like this, okay? ranges of the speed that your car will probably be going at. Well, it's unlikely that, sorry, it's unlikely that your car will be going faster than the speed of light. Or if it is, there's probably a bug in the software rather than the car actually traveling that quickly. Likewise, you will probably be moving slightly faster than 1 Planck length per second, or if you're moving more slowly than that, and questioning how you're measuring it. So one really big problem in verifying things with floating point is that the actual ranges that people want to use, the actual ranges that make anything like sense in the human world, are tiny compared to things that floats can represent. Like a double is, you know, the significand bits on it are 2 to the, you've got what, 53 bits, right? You know, that means the number of floating point numbers between 1 and 2 is 2 to the 53, which is, you know, certainly more people than will have ever lived. It's not quite up to the sort of number of atoms in a star kind of thing, but it's a horrendously big number. So the reason that floats have all of this extra accuracy and extra precision is that it allows them to handle computations accurately, because you said about rounding. So what it means is that they can avoid rounding until they have to, or the amount they round is very, very small. Anyway, as a consequence, if you're doing verification of software and verification involving floating point, be prepared for the fact that your system can reason, the code you're verifying can measure things and compute things more accurately than makes sense in almost any human scale. Like, that's something you're just gonna have to deal with, right? You know, so example, between 1 and -1 is half of all floats. So, you know, people tend to do things like, oh, this number, it's between 0 and 1. And then they act like that really narrows it down. I'm like, yeah, it's about a quarter of all floats are between 0 and 1. It's not a particularly useful range. Another consequence of this is that the specifications, trying to get people to write spec about floating point is really hard, because it's got all this extra precision, this extra detail. People, you know, often you'll generate some counterexamples, you go, look, your code, this could happen, and people say, yeah, but like no one would ever feed that in. That's not relevant, you know, that's the car speed that goes in there, it won't ever be that number. Okay, well, how do you write down it probably won't be that as a precondition? I don't know, to me, this is still a big unsolved problem. If you're trying to verify, code with floating point in it, there's a real human dimension to it, and to my knowledge, no one's cracked it yet. So this is the joke for Sarah about standards, courtesy of XKCD. Yeah, I think at this point, I kind of like to pause, because I think we're about 4 minutes away from a break. So maybe we could pause here and Sarab, do you want to say a bit about what's going to happen with this break?
So I think before we go on to break, there is one question.
Cool. Yeah, sure.
So, so Ashutosh is asking, the data coming from sensors like speed is limited by sensor sensitivity. They usually do not have large dynamic range. Is it not better to use fixed point representation for them?
Depends. But yeah, I mean, like if it was me, and I knew the range that I was working in, and I was building a sensor, I'd be tempted to return fixed point. I mean, there are other engineering concerns. If your sensor is particularly, it is particularly high performance, and the code that it's going into is going to use it as float, maybe it makes more sense to return float. But yeah, I think if I was building sensors, I'd probably have them return fixed point, but then I do the calculation in floating point, because that way the calculation is more accurate. But at least with the data gathering, then you know, you have a better feel for how accurate your numbers are. Yeah, fixed or input, float calculation.
Okay, so I believe now we can all move to Discord breakout rooms. So the breakout rooms also have voice and video channels. So if there is room 1, room 2, etc., I mean, you can join one of these. You can have in a close quarter have video chat, voice chat with other people. And so from the main Zoom meeting, we'll take a 30-minute break. We'll reconvene at 4:30 Indian Standard Time. Okay, so see you all on Discord.
One last thing. So part of the reason that in the last break I got everyone to post who they are and what they're interested in is now, if you're feeling lonely, if you don't know who to talk to, if you only know a few people here, go to the general channel, have a look down list, and find someone who, if they said that's really cool and you don't know what it is, ask them. If they said, hey, I'm working on that and it's something similar, ask them. So you now have ready-made introductions.